Unbundling databases. At a most abstract level, databases, Hadoop, and operating systems all perform the same functions. They store some data, and they allow you to process and query that data. A database stores data in records of some data model rows in tables, documents, vertices in a graph, etc., while an operating system's file system stores data in files, but at their core, both are information management systems. As we saw in Chapter 10, the Hadoop ecosystem is somewhat like a distributed version of Unix. Of course, there are many practical differences. For example, many file systems do not cope very well with a directory containing 10 million small files, whereas a database containing 10 million small records is completely normal and unremarkable. Nevertheless, the similarities and differences between operating systems and databases are worth exploring. Unix and relational databases have approached the information management problem with very different philosophies. Unix viewed its purpose as presenting programmers with a logical but fairly low-level hardware abstraction, whereas relational databases wanted to give application programmers a high-level abstraction that would hide the complexities of data structures on disk, concurrency, crash recovery, and so on. Unix developed pipes and files that are just sequences of bytes, whereas databases developed SQL and transactions. Which approach is better? Of course, it depends what you want. Unix is simpler in the sense that it is a fairly thin wrapper around hardware resources. Relational databases are simpler in the sense that a short declarative query can draw on a lot of powerful infrastructure query optimization, indexes, join methods, concurrency control, replication, etc., without the author of the query needing to understand the implementation details. The tension between these philosophies has lasted for decades. Both Unix and the relational model emerged in the early 1970s and still isn't resolved. For example, I would interpret the NoSQL movement as wanting to apply a Unix-esque approach of low-level abstractions to the domain of distributed OLTP data storage. In this section I will attempt to reconcile the two philosophies in the hope that we can combine the best of both worlds. Composing data storage technologies. Over the course of this book we have discussed various features provided by databases and how they work, including secondary indexes, which allow you to efficiently search for records based on the value of a field. See other indexing structures on page 85. Materialized views, which are a kind of pre-computed cache of query results. See aggregation, data cubes and materialized views on page 101. Replication logs, which keep copies of the data on other nodes up to date. See implementation of replication logs on page 158. Full text search indexes, which allow keyword search in text. See full text search and fuzzy indexes on page 88 and which are built into some relational databases. In chapters 10 and 11, similar themes emerged. We talked about building full text search indexes. See the output of batch workflows on page 411. About materialized view maintenance. See maintaining materialized views on page 467. And about replicating changes from a database to derived data systems. See change data capture on page 454. It seems that there are parallels between the features that are built into databases and the derived data systems that people are building with batch and stream processors. Think about what happens when you run create index to create a new index in a relational database. The database has to scan over a consistent snapshot of a table, pick out all of the field values being indexed, sort them, and write out the index. Then it must process the backlog of writes that have been made since the consistent snapshot was taken, assuming the table was not locked while creating the index, so writes could continue. Once that is done, the database must continue to keep the index up to date whenever a transaction writes to the table. This process is remarkably similar to setting up a new follower replica. See setting up new followers on page 155, and also very similar to bootstrapping change data capture in a streaming system. See initial snapshot on page 455. Whenever you run create index, the database essentially reprocesses the existing dataset as discussed in reprocessing data for application evolution on page 496 and derives the index as a new view onto the existing data. The existing data may be a snapshot of the state rather than a log of all changes that ever happened, but the two are closely related. See state, streams, and immutability on page 459. In this light, I think that the data flow across an entire organization starts looking like one huge database. Whenever a batch, stream, or ETL process transports data from one place and form to another place and form, it is acting like the database subsystem that keeps indexes or materialized views up to date. Viewed like this, Batch and stream processors are like elaborate implementations of triggers, stored procedures, and materialized view maintenance routines. The derived data systems they maintain are like different index types. For example, a relational database may support B-tree indexes, hash indexes, spatial indexes, see multi-column indexes on page 87, and other types of indexes. In the emerging architecture of derived data systems, instead of implementing those facilities as features of a single integrated database product, they are provided by various different pieces of software, running on different machines, administered by different teams. Where will these developments take us in the future? If we start from the premise that there is no single data model or storage format that is suitable for all access patterns, I speculate that there are two avenues by which different storage and processing tools can nevertheless be composed into a cohesive system: federated databases. Unifying reads: it is possible to provide a unified query interface to a wide variety of underlying storage engines and processing methods, an approach known as a federated database or PostStore. For example, PostgreSQL's foreign data wrapper feature fits this pattern. Applications that need a specialized data model or query interface can still access the underlying storage engines directly, while users who want to combine data from disparate places can do so easily through the federated interface. A federated query interface follows the relational tradition of a single integrated system, with a high-level query language and elegant semantics, but a complicated implementation. Unbundled databases. Unifying writes. While federation addresses read-only querying across several different systems, it does not have a good answer to synchronizing writes across those systems. We said that within a single database, creating a consistent index is a built-in feature. When we compose several storage systems, we similarly need to ensure that all data changes end up in all the right places, even in the face of faults. Making it easier to reliably plug together storage systems, for example through change data capture and event logs, is like unbundling a database's index maintenance features in a way that can synchronize writes across disparate technologies. The unbundled approach follows the Unix tradition of small tools that do one thing well, that communicate through a uniform low-level API pipes, and that can be composed using a higher-level language, the shell. Federation and unbundling are two sides of the same coin, composing a reliable, scalable, and maintainable system out of diverse components. Federated read-only querying requires mapping one data model into another, which takes some thought, but is ultimately quite a manageable problem. I think that keeping the writes to several storage systems in sync is the harder engineering problem, and so I will focus on it. The traditional approach to synchronizing writes requires distributed transactions across heterogeneous storage systems, which I think is the wrong solution. See derived data versus distributed transactions on page 492. Transactions within a single storage or stream processing system are feasible, but when data crosses the boundary between different technologies, I believe that an asynchronous event log with idempotent writes is a much more robust and practical approach. For example, distributed transactions are used within some stream processors to achieve exactly one semantic. See Atomic Commit Revisited on page 477, and this can work quite well. However, when a transaction would need to involve systems written by different groups of people, for example, when data is written from a stream processor to a distributed key-value store or search index, the lack of a standardized transaction protocol makes integration much harder. An ordered log of events with idempotent consumers, see idempotence on page 478, is a much simpler abstraction, and thus much more feasible to implement across heterogeneous systems. The big advantage of log-based integration is loose coupling between the various components, which manifests itself in two ways. At a system level, asynchronous event streams make the system as a whole more robust to outages or performance degradation of individual components. If a consumer runs slow or fails, the event log can buffer messages. See disk space usage on page 450, allowing the producer and any other consumers to continue running unaffected. The faulty consumer can catch up when it is fixed, so it doesn't miss any data, and the fault is contained. By contrast, the synchronous interaction of distributed transactions tends to escalate local faults into large-scale failures. See limitations of distributed transactions on page 363. At a human level, unbundling data systems allows different software components and services to be developed, improved, and maintained independently from each other by different teams. Specialization allows each team to focus on doing one thing well, with well-defined interfaces to other teams' systems. Event logs provide an interface that is powerful enough to capture fairly strong consistency properties due to durability and ordering of events, but also general enough to be applicable to almost any kind of data. If unbundling does indeed become the way of the future, it will not replace databases in their current form. They will still be needed as much as ever. Databases are still required for maintaining state and stream processors, and in order to serve queries for the output of batch and stream processors, see the output of batch workflows on page 411 and processing streams on page 464. Specialized query engines will continue to be important for particular workloads. For example, query engines in MPP data warehouses are optimized for exploratory analytic queries and handle this kind of workload very well. See comparing Hadoop to distributed databases on page 414. The complexity of running several different pieces of infrastructure can be a problem. Each piece of software has a learning curve, configuration issues, and operational quirks, and so it is worth deploying as few moving parts as possible. A single integrated software product may also be able to achieve better and more predictable performance on the kinds of workloads for which it is designed, compared to a system consisting of several tools that you have composed with application code. As I said in the preface, building for scale that you don't need is wasted effort and may lock you into an inflexible design. In effect, it is a form of premature optimization. The goal of unbundling is not to compete with individual databases on performance for particular workloads. The goal is to allow you to combine several different databases in order to achieve good performance for a much wider range of workloads than is possible with a single piece of software. It's about breadth, not depth, in the same vein as the diversity of storage and processing models that we discussed in comparing Hadoop to distributed databases on page 414. Thus, if there is a single technology that does everything you need, you're most likely best off simply using that product rather than trying to re-implement it yourself from lower-level components. The advantages of unbundling and composition only come into the picture when there is no single piece of software that satisfies all your requirements. The tools for composing data systems are getting better, but I think one major part is missing. We don't yet have the unbundled database equivalent of the Unix shell, i.e. a high-level language for composing storage and processing systems in a simple and declarative way. For example, I would love it if we could simply declare MySQL Elasticsearch, by analogy to Unix pipes, which would be the unbundled equivalent of create index. It would take all the documents in a MySQL database and index them in an Elasticsearch cluster. It would then continually capture all the changes made to the database and automatically apply them to the search index, without us having to write custom application code. This kind of integration should be possible with almost any kind of storage or indexing system. Similarly, it would be great to be able to pre-compute and update caches more easily. Recall that a materialized view is essentially a pre-computed cache, so you could imagine creating a cache by declaratively specifying materialized views for complex queries, including recursive queries on graph. See graph-like data models on page 49 and application logic. There is interesting early-stage research in this area, such as differential data flow, and I hope that these ideas will find their way into production systems.